Hello friends, welcome to a new video of our crash program or revision classes for physics for NEET and JEE. The chapter is mechanical properties of solids. This is the unit number 8. The first point we are discussing in this chapter is interatomic force between atoms. Okay. When atoms are at a large distance, there is a small interatomic attraction. As distance decreases, that interatomic attraction, that attractive force increases. Attractive force is always negative, represented as negative. As distance decreases, attractive force increases, and at a particular distance, that distance is called critical distance. That distance is called critical distance x. The attractive force becomes maximum, and the distance, if the distance again decreases less than x, the attractive force starts decreasing rapidly. And at a particular distance called equilibrium distance, or we will say mean distance between atoms, the attractive force becomes zero. And after that, if the distance again decreases less than r0, the interatomic force becomes repulsive, and the repulsive force increases more rapidly. That is what you are seeing in the diagram. Okay, once more, if this is the force displacement graph, at large distance the force is attractive, negligible attraction. As distance decreases, that attraction increases, and it reaches to a maximum value. That distance is called critical distance x. After that, this force starts decreasing rapidly, and at a particular distance, that distance is called equilibrium distance or mean distance, the force becomes zero. At mean distance, interatomic force is zero. And if the distance again decreases less than r0, the force becomes repulsive, and the repulsive force increases more rapidly. Okay. Attractive forces are represented as negative, and repulsive forces are represented as positive. This is the graph between interatomic force and the displacement between the atoms. Okay. If the distance is less than r0, we can say force is repulsive. If the distance is greater than r0, the force is attractive. So interatomic force may be repulsive or attractive according to the displacement between the atoms, and the interatomic force is zero at the equilibrium distance. Interatomic potential energy due to interatomic force. Potential energy, we studied that U equal to minus integral f dot dx or f dot dr. Okay. When the net force is zero, that means the system is in physical equilibrium, then potential energy U will be minimum. That means when force is zero, potential energy should be minimum. So when we are drawing the graph of potential energy and distance, potential energy versus distance, then we will get minimum potential energy when the force is equal to 0. Force becomes 0 when the distance is r0. Okay, then we can say at r0 potential energy will be minimum. Minimum means its value is negative and its magnitude is very large. Okay, so shape of potential energy graph will be like this. Why? When force is 0, potential energy should be minimum. So graph of potential energy versus distance between atoms is shown like this. We can compare the both the graphs. Okay, at r0 force is 0 but potential energy is minimum. That is the comparison between interatomic force and interatomic potential energy. Reason for elasticity. Atoms are bound with very strong interatomic force in solids, and molecules are also bound with a very strong intermolecular force. Okay. Behavior of intermolecular force is just like interatomic force. That means above an equilibrium distance, intermolecular force is attractive, and below the equilibrium distance, intermolecular force is repulsive. But strength of intermolecular force is very small when compared with the strength of interatomic force. Now listen here. When a body is acted, when a stress or when a force is applied on a body, then what happens? Body compresses. The distance between the molecules become less than the equilibrium distance. Then if the distance is less than the equilibrium distance, their intermolecular force becomes repulsive. Then due to that intermolecular force, a restoring force develops there, and the molecules tend to regain their original condition. That is the reason for elasticity. When we are stretching a material, then distance between the molecules increases than the equilibrium distance. So the intermolecular force becomes attractive, and that due to that intermolecular force, a restoring force develops in the solids, and the molecule regains their original position. Okay, in short we can say intermolecular force acts as a spring force, so they possess the material, the solids possess elasticity. Spring action of intermolecular force is the reason for elasticity. Stress and strain. What is stress? The restoring force developed per unit area due to the intermolecular force after the removal of deforming force. Restoring force developed per unit area. Restoring force developed per unit area. So, for a perfect elastic body, the magnitude of restoring force is equal to that of the deforming force. That means the molecules will reach to their original conditions. Perfect elastic bodies. For perfect elastic bodies, and for perfect plastic bodies, the intermolecular force will not have spring action. That means the restoring force will be 0, then the stress will be 0. Okay. And what is a strain? Strain is the fractional change in configuration. Fractional change in configuration. Fractional change means change by original. Change in configuration by original configuration. Change in configuration by original configuration. Okay. Strain is of 3 types and stress also 3 types. Okay. Stress which changes length is called longitudinal stress or linear stress, force by area. Okay. Stress which changes the volume is called volume stress or bulk stress, and stress which changes shape of the body is called tangential stress or shear stress. And change in configuration by original configuration, strain, is also 3 types: longitudinal or linear strain, volume or bulk strain, tangential or shear strain. Okay. Stress is actually force by area. Okay. And change in configuration by original configuration for linear strain. For linear strain, we will say change in length by original length. Okay, linear strain is also called longitudinal strain. And for volume strain, what is volume strain? Volume strain is also called bulk strain. Volume strain or bulk strain means change in volume by original volume. And what is shear strain or tangential strain? We can't say change in shape by original shape, because shape is not a physical quantity. Shape is not a physical quantity. So, for tangential strain or shearing strain, there is a special definition that you have to listen carefully here. A block whose one side is fixed and the opposite side gets a tangential force. The opposite side gets a tangential force. Then the upper part of the body displaces, but the lower part remains at the same position. Okay. If this is the x is the linear displacement of the opposite part of the fixed side, and L is the perpendicular length of the fixed part, then this theta is the shear strain or tangential strain. That means theta is defined as tangential strain or shear strain is defined as the angular displacement. Shear strain is defined as the angular displacement of a plane perpendicular to a fixed surface, under the application of or due to the application of tangential force. Shear strain, here we can take tan theta. Tan theta equal to opposite side by hypotenuse. Hypotenuse I am giving it here it as L dash. So we can say if theta is very small, then tan theta approximately equal to theta. And L dash approximately equal to L. If theta is very small, this L dash and L will be almost equal. So we can rewrite this as theta equal to x by L. This is the tangential strain or shear strain. Linear strain means change in length by original length. Volume strain means change in volume by original volume. Tangential strain or shear strain means what? Angular displacement of a perpendicular plane, which is angular displacement of a plane perpendicular to a fixed surface due to the application of a tangential force. Here you can see strain has no unit and no dimension. Strain has no unit and no dimension, but stress possesses unit and dimension. Stress means force by area, restoring force by area. So unit is Newton per meter square, or we will use it as Pascal, which is the same as unit of pressure. Here is a question. On suspending a weight mg, the length L of elastic wire and the area of cross section A, its length becomes double the initial length. The instantaneous stress action on the wire is, options are mg by A, mg by 2A, 2 mg by A, 4 mg by A. Just to pause the video and try to solve it. Okay. We are asked to find instantaneous stress. Instantaneous stress means the stress when length is doubled. Okay. Stress, we know that what? Force by area, restoring force by area. But here length is doubled, right? When length is doubled, then area becomes half of the original value. Why? We know that volume of a material is constant, area into length. A1 L1 equal to what? A2 L2. Initial area of cross section is A, initial length is L, equal to final area is A2 and final length is 2L, length is doubled. So we will get what? A2 equal to A by 2. New area is A by 2. So here instantaneous stress, restoring force by instantaneous area when length is doubled, that area we can write A2. So F by, we will get A by 2, 2 will go to the top, 2F by A, mg is the force, 2 mg by A is the instantaneous stress. But the stress applied at the beginning is what? F by A, mg by A. Mg by A is the stress applied. Applied stress equal to force by area. Area at the beginning, that is A, mg by A. This is the applied stress. And 2 mg by A is the instantaneous stress when area is halved or length is doubled. Okay, one more question. One end of a uniform wire of length L and weight W is attached rigidly to a point in the roof, and a weight W1 is suspended from its lower end. If S is the area of cross section of the wire, the stress in the wire at a height 3L by 4 from its lower end. W1 by S, W1 plus W by 4 all divided by S, W1 plus 3W by 4 upon S, W1 plus W by S. How to solve it? We already discussed that stress equal to what? Force by area. What are the forces acting at that point L by 4 from the top end or 3L by 4 from the bottom end? At L by 4 from the top end, at that point, the area of cross section is given as S in the question. And what are the forces acting there? Weight of weight W1, which is suspended from the wire, that will act W1 plus, and 3 by 4 of the weight of the wire, 3 by 4 of W. Why? At the point 3L by 4 hangs from that point and total weight is W. So for a uniform rod, weight is also uniform at every O. So we can say the weight of 3L by 4 is equal to 3W by 4. So total force acting at the point is W1 weight suspended W1 plus 3W by 4, 3 by 4th of weight of the rod by the area S. Option 4 is the right answer. Next, Hooke's law, Robert Hooke's law, the important law in elasticity. Hooke's law. Within the elastic limit, stress, the restoring force developed per unit area is proportional to strain in the material. Within the elastic limit, stress is directly proportional to strain. Okay. Elastic limit is the final point, the last limit of the body which shows elasticity. Above the elastic limit, body will not show elasticity, body will show plasticity. That means body will not come to the original condition. Okay. So within the elastic limit, we can say stress is proportional to strain according to Hooke's law. Then when we are drawing a graph, stress versus strain graph, if they are directly proportional, the shape of the graph will be straight line inclined to both the axes. Okay. So we can say stress equal to a constant into strain. A constant into strain. That constant E equal to what we can say stress by strain. Stress by strain. This constant is called coefficient of elasticity or modulus of elasticity. Coefficient of elasticity or modulus of elasticity. Then you take slope of the graph, stress strain graph. Slope will be tan theta, opposite side by adjacent side, stress by strain. So we can say slope of stress strain graph is what? Elasticity. Slope of stress strain graph gives elasticity. Here tan theta equal to elasticity. That means as slope increases, elasticity increases. As slope increases, elasticity increases. Value of E, modulus of elasticity, depends on temperature. That means as temperature increases, intermolecular force decreases. Intermolecular force decreases because molecules will get more kinetic energy. So intermolecular force will decrease as temperature increases. Then elasticity decreases. Elasticity decreases. And value of E is different for different materials. Value of E is different for different materials. And value of E does not depend on the dimensions or size of the material. For a material, value of E, modulus of elasticity, is constant at a particular temperature. It is independent of its length, shape, mass, dimensions. Okay. And value of E depends on the manner how the stress is applied. For example, we can apply linear stress on the body, then the strain produces linear strain. So modulus of elasticity equal to linear stress by linear strain. That is what called Young's modulus. And volume is changed, then we will say volume stress by volume strain, that is bulk modulus. And if shape is changed, we will say modulus of rigidity or rigidity modulus, shear modulus. It is tangential stress or shear stress by tangential strain or shear strain. That's why I told you value of E depends on the manner how the stress is applied. Modulus of elasticity or elasticity equal to stress by strain, for the same strain. Modulus of elasticity is proportional to stress. That means as stress increases, modulus of elasticity increases. For example, we have a steel rod and a rubber band. Steel rod and a rubber band of identical dimensions. And we are applying a stress on the two rods. I made a particular strain in rubber rod. For example, change in length of 10 centimeter in a rubber rod, in a rubber band. And I am trying to give the same change in length in steel rod also. Then I have to give more stress on the steel rod. Then we can say elasticity of steel is greater than elasticity of rubber. Once more, for the same strain, to produce same strain, if you are compelled to apply more stress, then the body is more elastic according to Hooke's law. As stress increases, elasticity increases for the same strain. So in steel rod and in rubber band, for the same strain, more stress to be applied in the steel rod. So we can say elasticity of steel is greater than elasticity of rubber. Elasticity of steel is greater than elasticity of rubber. So we can say steel is more elastic than rubber. Steel is more elastic than rubber. So when we are drawing stress strain graph of steel and rubber, we will get two lines. This is of rubber and this is of steel, because slope of steel will be large. Okay. Young's modulus. Young's modulus means linear stress by linear strain or longitudinal stress by longitudinal strain. Linear stress by linear strain. That is why stress is always taken as restoring force by area, and linear strain is delta L by L, change in length by original length, or y equal to, we will get FL by A delta L. FL by A delta L. So change in length, elongation or compression, delta L equal to, we can say FL by YA. FL by YA. And for circular cross section, for a rod having circular cross section, we can say area of cross section as pi r square. So we can say FL by Y pi r square. If the same force is applied for different wires of same material, once more, same force is applied for different wires of the same material, then we can say elongation delta L proportional to L by R square. Elongation delta L proportional to L by R square for the same force and same material. For a material Y is constant. So we are applying the same force for two different iron rods. Two different iron rods. Material is same, then Y is same. So in which wire, in which rod elongation is maximum and in which rod elongation is minimum, that we can find using L by R square. As L by R square is maximum, change in length will be maximum. Okay. Once more, we can say here we can write the condition: same material, same force. Then we can use delta L proportional to L by R square. Okay. Now this equation delta L equal to, I am just multiplying the numerator and denominator with length L. Okay. So FL by YA, we will get FL square by Y into area length. Area into length denotes volume. So we can say FL square by Y volume. Area into length is volume, right? Like that, delta L equal to, and in the same equation I am multiplying numerator and denominator with the area. Numerator and denominator with the area. Then I will get FL into A. Length into area, volume. Volume will come on numerator. YA square. Okay. In first case I multiplied with the length on numerator and denominator. In second case I am multiplying numerator and denominator with the area. So F into length into area will get volume. So we can say delta L equal to force into volume divided by Y into area square. Y into area square. So from these two equations we can say same material, same force and same volume. Same material, same force and same volume. Then we can say change in length is proportional to L square, or change in length is proportional to 1 by A square. If length of a wire is doubled, what will be the linear strain? Strain is change in length by original length. Change in length means final length L dash minus original length divided by original length. Final length minus initial length. Length of wire is doubled, then final length will be 2L. 2L minus L by L. We will get what? L by L. That is 1. So if length of a wire is doubled, then linear strain is 1. If you are converting it into percentage, you will get 100% change in length, because length is doubled. So there is 100% change in length, elongation. Now, then what is Young's modulus relation? Linear stress by linear strain. Linear stress by linear strain. Here linear strain equal to 1. So we can say Y equal to what? Linear stress. Y equal to what? Linear stress. So we can say a definition for Young's modulus. Young's modulus is the stress which produces 100% change in length, or Young's modulus is the stress which doubles the length of a rod. Okay, that is the definition of Young's modulus. Force constant of a wire. We know that for a rubber band or an elastic body, as external force acts, its length changes. When length is changed, a restoring force acts inside the body, inside the material, due to the spring action of intermolecular force. So we can say that restoring force F equal to minus Kx, as we discussed in the case of spring, or F equal to, here we are discussing X as how delta L, change in length, okay, restoring force. And when we are taking its magnitude, we will get F equal to what? K into delta L. And what is the equation we studied here just now? Y equal to FL by A delta L, then F equal to what? Y A by L into delta L. Y A by L into delta L. This is equation of force. So when we are comparing these two equations, equation number 1 and equation number 2, here we took the magnitude only. So we can see, instead of K, who is coming, the YA by L. This K is called force constant of a wire. K equal to YA by L. Force constant depends on the dimensions of the material, area of cross section, length of the wire, and the nature of the material. Y is the right, but Y is independent of, elasticity is independent of dimensions of the or size and shape of the material, but K, force constant, depends on the shape and size of the material, okay, and also on the nature of the material, okay. So from here we can say force constant K equal to the restoring force developed per unit length. Force constant K equal to the restoring force developed per unit length, and that is found using equation YA by L, okay. Due to a force or a tension T1, length becomes L1, length of a wire becomes L1, and due to another tension T2, length of a wire becomes L2. Then what will be the actual length of the wire? Okay, that equation we have to find. When a force is, deforming force is acting on the body, we can say new length equal to old length or original length plus or minus change in length. The force is, the stress is tensile stress. Tensile stress means the stress which increases length of the body. Then the new length will be old length plus the extra length. If the stress is compressive, that means which reduces the length, then we have to write L minus delta L. Okay, length will decrease. Okay, so we can say L1 equal to actual length plus or minus delta L1. Actual length L plus or minus delta L1. And in second case also we can write actual length plus or minus delta L2. Here we are taking both the tensions or forces are tensile, which increases length, so we can consider only plus. Okay, we just discussed that F equal to K delta L or Kx, then delta L equal to what? F by K. Delta L equal to what? F by K. So instead of delta L1, we can use first tension 1 by constant K. So we will get two equations there. L1 equal to L plus T1 by K, equation number 1, and L2 equal to L plus T2 by K, equation number 2. From these two equations, we can find the equations of K and L, force constant and actual length, by solving these two equations. First, equation number 2 minus 1. I am taking subtracting 1 from 2. As I am assuming that tension T2 is bigger. That's why I am subtracting 1 from 2. If T2 is bigger, L2 will be bigger, right? Okay. Or you can do 1 minus 2 also. No problem. So 2 minus 1, we will get L2 minus L1 equal to what? L2 minus L1 equal to, L will be cancelled, T2 by K minus T1 by K. So I can write T2 minus T1 into 1 by K. T2 minus T1 into 1 by K. Then what is 1 by K? 1 by K equal to L2 minus L1 by T2 minus T1. It is 1 by K. This equation of 1 by K, I am giving this as equation number 3. We can substitute in equation number 1 or equation number 2 to get actual length L. So I am applying 3 in 1. 3 in 1. L1 equal to L plus T1 by K. For 1 by K, I can use L2 minus L1 by T2 minus L. So L2 minus L1 by T2 minus T1. So we will get L equal to L1 minus T1 L2 minus, in bracket, T1 L2 minus T1 L1 divided by T2 minus T1. Okay, L equal to L1 T2 minus L1 T1 minus L2 T1 plus L1 T1 all divided by T2 minus T1. What I did is just I crossed and here bracket is opened. L1 T2 minus L1 T1 here plus L1 T1, it is cancelled. L1 T2 minus L2 T1 divided by T2 minus T1. L equal to L1 T2 minus L2 T1 divided by T2 minus T1. This is the actual length. Once more, the question is, at a tension T1, length of a wire becomes L1, and at a tension T2, due to a tension T2, length of a wire becomes L2. Then what will be the actual length? Actual length is L1 T2 minus L2 T1 divided by T2 minus T1. Or you can say L2 T1 minus L1 T2 divided by T1 minus T2. Actual length is always positive, right? And here, then what will be K? Force constant. 1 by K we will get L2 minus L1 by T2 minus T1. Then K, force constant, will be T2 minus T1 by L2 minus L1, or T1 minus T2 by L1 minus L2. Here is a question. The length of an elastic string is A meters when the longitudinal tension is 4 Newton and B meters when the longitudinal tension is 5 Newton. Length of the string in meters when the longitudinal tension is 9 Newton. Options are the A minus B, 5B minus 4A, 2B minus 1 by 4A, 4A minus 3B. Just to pause the video and try to solve it. Okay, 3 cases are here. Length becomes A meters when the tension is 4 Newton. A when the tension is 4 Newton. B when the tension is 5 Newton. Then what will be length when the tension is 9 Newton? So we have to calculate L3 in terms of A and B. We have to calculate L3 in terms of A and B. What will be length L3 equation? Actual length plus the extra length in third case, delta L3. L plus that delta L3 we can write T3 by K. What is T3? Tension in third case. This is T1, here 5 Newton is T2 and 9 Newton is T3. Ambulance. Okay, here we can find L and K using the equations that we already studied. What is L equation? L1 T2 minus L1 T2 minus L2 T1 divided by T2 minus T1. What is L1 T2? L1 is A, L2 is B. L1 T2 5A minus what is L2 T1? B4B divided by what is T2 minus T1? 5 minus 4, it is 1. So we got actual length 5A minus 4B, that we can give here, 5A minus 4B plus what is T3? T3 is 9 into, we have to find K, 1 by K. What is K equation? K equal to what? T2 minus T1 by L2 minus L1. What is T2? 5 minus 4, 1 by L2 minus L1, B minus A. K is 1 by B minus A. So 1 by K is B minus A. So we can write here B minus A. Here 5A, 9 into minus A, minus 9A. So there is minus 4A. Minus 4A minus 4B plus 9B. So 5B. Answer is 5B minus 4A. What is the answer? Which is the correct option? Option B is the right answer. Next side heading, elastic potential energy. Elastic potential energy. We just discussed that case of elastic string is just like a spring. Okay. So the force we can write minus kxk as ya by L, x as delta L. So elastic potential energy is also u half kx square. Case of spring that we already discussed in the chapter work, energy, power. That chapter's link is given in the description box. Those who have doubts about the topic, you can watch that video. Okay, now listen here, u equal to half kx square. For k we can write what? Ya by L, and for x we can write delta L. This is the elastic potential energy, u equal to Ya by L into delta L square. No need of by-heading this. You just by-head u equal to half kx square. What is k? Ya by L. Okay, and you know that f equal to what? Kx. For k you can write f by x. For k you can write f by x. So this equation you can rewrite. U equal to what? For k you can write f by x. F by x into x square. 1x will be cancelled. U equal to half fx. For x you can write what? Delta L. Half f delta L. This is one condition. And from here also you can write x equal to what? F by k. X equal to what? F by k. For x you can give f. So f square by k square. F square by k square. 1k will cancel. So you will get u as what? U equal to f square by 2k. F square by 2k. What is energy density? For energy density you can give ED or UD. Just to understand energy density. Energy density means energy by volume. Potential energy by volume. For potential energy we studied different equations. I am taking that simplest equation, half fx. Or you can use half kx square also. Okay. Half fx. For volume, we can write area into length. L. For volume, I can write area into length. Half into force by area is stress. And what is X? X is change in length. Change in length by original length is strain. Change in length by original length is strain. This is energy density of the elastic material. Half into stress into strain. You can see here what? According to Hooke's law, stress strain graph is straight line inclined to both the axes because stress is directly proportional to strain. So, slope gives what? What is slope? Slope gives modulus of elasticity, tan theta, that we discussed. And what is the area of the graph? Area under the graph we will get a triangular shape, right? What is the area of triangle? Half into length into half BH, half into base into height, half into base into height. What is base strain? What is height stress? Half into stress into strain, half into stress into strain. What is that? Energy density. So, area under stress strain graph is energy density or energy by volume, U by V. Slope of stress strain graph is elasticity. Area under stress strain graph is energy density or energy by volume. So to find energy, we can multiply area of the graph into volume of the material. Area of the graph into volume of the material. Okay, that area of the graph will be half into stress into strain. So energy density equal to half into stress into strain. Now listen here, right? Strain has no unit, no dimension, right? Stress has unit and dimension. Force by area, Newton per meter square or Pascal. Energy density has same unit of stress, same dimensional formula of stress. Like that modulus, elastic modulus, elasticity is stress by strain. Young's modulus, bulk modulus, rigidity modulus, all are stress by strain. Strain has no unit and dimension. So we can say Young's dimensional formula of Young's modulus equal to dimensional formula of bulk modulus equal to dimensional formula of rigidity modulus equal to dimensional formula of energy density equal to dimensional formula of stress equal to dimensional formula of pressure. These all quantities have same unit, same dimensions. Y equal to what? Stress by strain. Stress by strain. So for stress we can write Y into strain. For stress I can write Y into strain. So energy density I can write half into Y into strain, half Y strain square. One more equation for energy density. Like that, for strain I can write stress by Y. For strain I can write stress by Y. So half into stress by Y. So we will get what? Stress square by 2Y. Stress square by 2Y. Bulk modulus means volume stress by volume strain, volume or bulk stress by bulk strain, volume stress by volume strain. Stress is force by area and volume strain is change in volume by original volume. Change in volume by original volume. B equal to minus P by delta V by V or minus PV by delta V. Minus PV by delta V. Here P means change in pressure or extra stress used to produce the volume strain. Not all the pressures present. For example, a spherical body equal forces applied normal to the surface at all points, then volume of the sphere decreases. Volume of the sphere decreases because equal forces are applied perpendicular to the point of application. At all point that force is perpendicular. Then volume of the body decreases. Okay, if pressure decreases, volume increases. Then the applied stress is P, force by area. Applied pressure is the force by area, or P, that delta P. Not all the pressures present there. There may be atmospheric pressure. We are not taking atmospheric pressure into consideration. Gases possess 4 elastic modulus, 4 bulk modulus. Okay. Isothermal bulk modulus or isothermal elasticity, adiabatic elasticity or adiabatic bulk modulus, isobaric elasticity or isobaric bulk modulus, isochoric elasticity or isochoric bulk modulus. That means elasticity of gases changes according to the process. Okay. In isothermal process, we studied that PV equal to constant, pressure into volume equal to constant. So applying method of partial differentiation, first into derivative of second plus second into derivative of first, P dV plus V dP equal to 0. Okay. P dV equal to what? Minus V dP. Okay. From here, you see P equal to what? Minus dP by dV all divided by V. dP is change in pressure, minus delta P by dV divided by V, or delta V by V. Delta P by delta V by V, or PV by delta V, it is actually bulk modulus. So we can say isothermal bulk modulus is equal to pressure. Isothermal bulk modulus or isothermal elasticity is equal to pressure. And what about adiabatic elasticity? What was the equation of adiabatic process? PV raised to gamma equal to constant. PV raised to gamma equal to constant. What is gamma? Gamma is ratio of specific heat, Cp by Cv. I am not going into the proof, but I am telling the equation directly. Adiabatic elasticity equal to gamma into pressure. Adiabatic elasticity equal to gamma into pressure. Okay. What about isobaric elasticity? In isobaric process, bulk modulus equation is delta P by delta V by V. Here is a negative, say. Okay. In isobaric process, no change in pressure. Pressure is constant, so delta P will be 0. When delta P is 0, isobaric elasticity is 0. So isobaric elasticity for a gas is 0. That means in isobaric process, gas will not show elasticity. Okay. And isochoric elasticity, in isochoric process, change in volume is 0. Volume is constant. When change in volume is 0, it comes on denominator. So bulk modulus will be infinity. EV equal to infinity. EV equal to infinity. That means gases possess infinite elasticity during isochoric process. Here is a question. A uniform cube is subjected to volume compression. If each side is decreased by 1%, then bulk strain is, options are 0.01, 0.06, 0.02, 0.03. Volume compression, volume is decreasing, but linear strain is given as 1%. What is the equation of volume? Volume equal to, for a cube, It is side cube, L cube. Okay. So change in volume by original volume, percentage change in volume equal to 3 into change in length by original length. From here we can say volume strain of a cube is equal to 3 into linear strain. Volume strain of a cube is equal to 3 into linear strain. Linear strain is given in percentage, right? So volume strain is also in percentage 3%. 3 into 1%, it will be 3%. In question there is no percentage. 0.003 is the answer. How to remove percentage? Just divide with 100. We will get 0.03. To make percentage, you have to multiply with 100. To remove percentage, you have to divide with 100. So 0.03 is the answer, option 4. Okay, next. Shear modulus. Shear modulus, or we can say rigidity modulus. Rigidity modulus. Symbols given are eta or g. Can give eta or g for rigidity modulus. Shear modulus means, rigidity modulus means shear stress by shear strain, or tangential stress by tangential strain. That is, F by A by shear stress is defined as theta, angular displacement of a perpendicular plane. Okay, FA by theta, or we can say F by A theta. For theta we can say F by A into theta is X by L, X by L. Change in shape without change in volume. Change in shape without change in volume. So theta will be very small. If theta is large, there will be shear strain and volume strain also. That's why we set the condition initially, the theta will be very small. So tan theta equal to theta and L dash approximately equal to L when we are discussing shear strain. Okay. Poisson's ratio. Letter is sigma. Poisson's ratio. Okay. It is not a modulus of elasticity, but to discuss the relation between different moduli elasticity Y, B and G, we need to know who is or what is Poisson's ratio. Okay. Poisson's ratio means, equation is what? Lateral strain by linear strain. Lateral strain by linear strain. This is the equation for Poisson's ratio. Okay. What is lateral strain? For a rod of circular cross section. For a rod of circular cross section, using a force, if its length, when its length increases, its radius decreases. When length increases, the wire becomes thinner. Okay, so radius decreases. And if we are compressing that wire, what will happen? Its length will decrease, then area increase because volume remains constant. So length increases, then radius decreases. Then what is lateral strain? Lateral strain is change in radius by original radius. Strain in the radius of wire. That is called lateral strain. Change in radius by original radius. Fractional change in radius. Okay. Then the ratio lateral strain by linear strain is called what? Sigma or Poisson's ratio. Its relation is written by sigma equal to delta R by R by delta L by L. Delta R by R by delta L by L, and it is always taken as negative. Why? As length increases, radius decreases. As length decreases, radius increases. So sigma is normally taken as negative. And value of sigma lies between 0.5 and 0. Relations between elastic moduli y, b and g. First relation, y equal to 3b into 1 minus 2 sigma. Second relation, y equal to 2g into 1 plus sigma. Third relation, 9 by y equal to 1 by b plus 3 by g. These are the relations between y, b and g. And we will get one more relation by comparing 3b into 1 minus 2 sigma equal to 2g into 1 plus sigma. Okay. Then we will get a fourth relation. Sigma equal to, that is Poisson's ratio is equal to what? From equation number 1 and 2, we will get equation for sigma in terms of g and b. How? 3b minus 6b sigma equal to 2g plus 2g sigma. Equating these two equations, okay. Y, both 1 and 2 are y. So 3b into 1 minus 2 sigma equal to 2g into 1 plus sigma, and breaking the bracket. 3b minus 6b sigma equal to 2g plus 2g sigma. Okay. 3b minus 2g equal to 6b plus 2g into sigma. 6b plus 2g into sigma, taking sigma outside. So we will get sigma equal to what? 3b minus 2g by 6b plus 2g. 3b minus 2g by 6b plus 2g. This is equation of sigma. 3b minus 2g by 6b plus 2g. First relation is relation between Young's modulus and bulk modulus. Second relation between Young's modulus and rigidity modulus. Third relation between three moduli y, b and g. And fourth relation we can say relation between b and g. You can see a table here. Young's modulus, bulk modulus, rigidity modulus, solids, liquid, gases. For solids we can change its length, volume, shape using a stress. So we can discuss bulk modulus, Young's modulus, rigidity modulus for solids. And for liquids and gases, we can discuss only change in volume using a stress. No length and shape is defined for liquids and gases. When the same stress are applied in solids, liquids and gases, then strain in solids will be very small and strain in gases will be large. So we discussed that as strain increases, elasticity decreases for the same stress. So we can say bulk modulus of solids greater than bulk modulus of liquids greater than bulk modulus of gas. Solids are more elastic than liquids and gases. Gas is less elastic than liquids and solids. Water is more elastic than air because water is liquid, air is gas. Okay. Depression in bridges. Depression means after a long time use, the center part of bridge will hang down, will move down little bit. Okay, due to a long use. Okay. The displacement between the initial condition position and final position, that is what called depression. In rectangular bridges, the depression is calculated using the equation WL cube by 4YBD cube. And in circular bridges used for water irrigation, okay, like that, that maximum depression is calculated using equation WL cube by 12Y pi r raised to 4. No need of the proofs, derivations, just by heart the equations. Then you can see, to minimize depression in bridges, rectangular bridges, whose depth should be decreased. depth should be increased, whose depth or thickness should be increased to get minimum depression. Okay, and in cylindrical bridges, radius should be increased to minimize depression. Here you can see stress strain graph. This is the actual shape of the graph. You can see a region there, OP. OP region is the region where Hooke's law is obeyed. Hooke's law is obeyed because stress is proportional to strain, straight line. P is the proportionality limit. But after that also body shows elasticity up to E. PE also elastic region but not linear. That means that portion does not come under Hooke's law. Because Hooke's law says what? Within the elastic limit, stress is proportional to strain. But this is the actual graph of materials. So OP actually obeys Hooke's law. From P to E, Hooke's law is not obeyed, but the region is elastic. Body shows elasticity. Okay, where E is the elastic limit and P is the proportionality limit up to which Hooke's law is obeyed. After E, body shows plasticity. That means body will not regain its original condition. When the strain increases greater than P, when the stress increases greater than elastic limit. Then shape of the graph will be different for different materials in plastic region. Okay, EA, BC, you can see there. EA, BC indicates plastic region. C is the fracture point or breaking point. That means at the point body will start to break, And what is B? Listen carefully here. When stress is increased, strain also increases. Body will not return back to its original position. It is plastic region. Okay. When stress is increased, strain also increases. Stress increases, strain increases to a maximum value. Then that maximum value of stress is marked there B. It is called breaking stress. B denotes breaking stress. We can say it as SB also, breaking stress. The stress after which body begins to flow or body begins to break. That maximum value of stress is called breaking stress, or it is also called what? Tensile strength. It is also called tensile strength. It is calculated using SB equal to breaking force by area. Breaking force is the maximum force which applies just to break the body. FB by area. So breaking force equal to, we can say, breaking stress into area. Breaking stress is constant for a material. So we can say breaking force proportional to area of cross section. Breaking force proportional to area of cross section. Area we can write pi r square for circular cross section. So it is proportional to radius square. So breaking force is independent of length of the wire. Breaking force is independent of length of the wire. So region EABC is plastic region and region OPE is elastic region. Okay. For ductile materials, plastic region will be very large as compared to elastic region, because we can make them into thin wires for ductile materials. And for brittle materials, plastic region will be very small. Their fracture point or breaking point lies very close to the elastic limit. Okay. And for elastomers, What are elastomer? Elastomers are rubber bands, elastic tissue of iota. That means we can stretch them to large lengths. But when the elastic limit is reached, they will break. Their elastic limit is same as at the fracture point. They do not have plastic region. Elastomers means materials which do not have plastic region. They have only the elastic region, and we can stretch them to large extensions, large lengths. But their fracture point lies at the elastic limit. They do not have plastic region like rubber, elastic tissue of iota in our heart. Okay, they are elastomers. Their graph is parabolic. So we can say elastomers do not obey Hooke's law at all. Elastomers do not obey Hooke's law at all. In Hooke's law, stress strain graph will be straight line. For elastomers, graph is not straight line, parabolic. They do not obey Hooke's law at all. Elastic hysteresis. Elastic hysteresis. Hysteresis means energy loss in the form of heat. Energy loss in the form of heat. Okay. When a rubber band is given a deforming force, then restoring force will develop inside it to regain the original condition. But the energy given by the work done given by the external force will not be completely converted into elastic potential energy. A part of the elastic potential energy losses in the form of heat. That is shown by elastic hysteresis. Okay. But elastic hysteresis indicates lagging of stress behind the strain in a cyclic elastic process. Lagging of stress behind the strain. It is shown by the elastic hysteresis curve. As area of hysteresis loop increases, energy loss increases, and area of hysteresis loop decreases, energy loss in the form of heat decreases. Okay. Here you can see two hysteresis loops, A and B, rubber A and rubber B. Okay, rubber A with a large hysteresis loop. That means rubber A can make loss of elastic potential energy in the form of heat in large amounts. So it is used to absorb vibrations of machinery parts in industry. In factories. Okay, you can see in some factories, machineries are placed above rubber sheets. If there is no such rubber sheet below the machinery parts, due to the vibration, parts of the machinery parts may be damaged, and the floor also may be damaged due to the vibration. That vibration can be absorbed by the rubber sheet and it is converted into heat. Okay, that happens using in the case of rubber A with a large hysteresis loop, and also in the case of rubber B with a small hysteresis loop. In short, rubber with a large hysteresis loop is used to avoid vibrations of machinery parts, and rubber with a small hysteresis loop is used to avoid excess of heating. So they are used to make tires of vehicles. The last point of the chapter, okay, a rubber cord catapult. Which is used to frighten birds, dogs, etc. Okay, placing stone above it and stretching. What happens? Its length increases. So elastic potential energy of the rubber cord is converted into kinetic energy for the stone. So we can say elastic potential energy is converted into kinetic energy for the stone. Elastic potential energy we can use half kx square. For kinetic energy we can use half mv square. Okay. Here k we can write Ya by n if Young's modulus and area of cross section length etc. are given. X is actually delta L. Okay. V is the velocity of the stone. But here also we can say the elastic potential energy given by the man will not be completely converted into kinetic energy for the stone due to elastic hysteresis. So kinetic energy will be less than the elastic potential energy if there is no any heat loss. Then we can say elastic potential energy completely converts into kinetic energy. Okay. This chapter, mechanical properties of solids, is over, finished here. I try to include all the concepts in this chapter. Study material with some entrance points, questions and solutions is given in the description box. You can download it, and if you are doing those questions, you will get a clear idea about the concepts of the chapter. Best of luck, stay safe.